Welcome back to Jogamers. Last video I showed you the equation for a sector between two, and you think, well, there's two integrals, and there's a lot of visualization of the graph. Why couldn't we why couldn't we go back to that circle integral and find the sector like that? First off, let me tell you something. The area of the circle accounts for the whole circle. Sectors are only the angle, alright? I would have to somehow remove this triangular portion of the circle that I didn't want, right? So you're gonna involve something like it's fine to get the area of the full circle because these lines count as a full circle, but as a sector, these lines really do make it hard to actually find the area of the equation of a sector. I mean, actually, just plug in the freaking equation here, and I think, yeah, like, I'm not gonna freaking go turn this entire function into, this entire thing into 1/2 theta r squared. Like, we're not doing it. Alright, also, why did I write R2? It's the same thing. Today's video, not today, it's just the same day, but this video is going to show, oh yeah, so first, we're gonna find the area inside the same quadrant, and then show that our final equation, not really equation, but just a way to, if I use the same xy from the sector, and it was a part of this larger sector, how can I make it the whole sector? You know what I'm saying? To make it shorter, make it not this short. So I did have to use two integrals. I think you still have to use two integrals in this, but the difference between getting the whole thing versus multiplying something from here to here is probably a lot more work if I'm being honest, but whatever. Anyways, so let's find the sector. Let's find this mini sector that's inside this other sector, right? So right here, from x1 to x3, what is the area of this sector? Well, holy crap, this line is so bad. Let me just have to draw. Okay, so we got the line. Stripe blue, and another six one here. Yeah, that's better. So, oops, that's the wrong color. Whatever. So, this is the sector we want. This is x3. So how are you gonna go about this? It's actually really simple. Just draw out your line again. So I should make this blue color, like this blue, and the next one is gonna be this. So yeah. So draw something like this. Draw your lines out again. Now, as you can see, there's gonna be two integrals. One integral to get this area right here, and one integral to get this area here. Alright, so let's draw an integral. So this position is from, or at least this area to here is from 0 to x3. And the functions involved are the two lines here, which is, I don't know this line, let's call it R3, and that line's the R1. So R3 minus this R, these two functions share the same area between here, but we want the area made by x3 and x1 to get that part of the sector, right? So from 0 to x3 we're gonna write since this line is the radius and we're using the circle function in x, so we're just gonna use the function. We're gonna do the same thing. We're gonna use the function of x3. Since this line is above this line, R3 is above R1. That means it's f of 3 x3 x minus f of x1 x dx. Alright? So those two lines from 0 to x3 create that portion. Now we have to get this portion right here, and as we can see, these two lines are from x1 to x3, and they encompass the only functions that have the area between here are the circle function and line of x or R1. So what we're doing for this is plus integral from x3 to x1, and we're getting the area from here to here. So since the circle and line of R1 both what's the word? The word is, they both have the same area, right? I don't know the word, the union. I think this is union, right? The in between is union, whatever. They union this area. They share the same area, but the function of the circle also has this area, and we're trying to find this area, so we do function minus line again. So f of x dx minus f of those R1 sign, so x1 over x1 x dx. So that was a quick way to find the area of this mini sector within this bigger sector. I mean, if it was just a different other sector like this new sector I'm drawing, same logic, that's before it makes the same freaking shape that you draw freaking lines out and you want this. So, yeah. Here's the equation for a sector in the same quadrant. Now, oops, I probably should have erased that. So now, that's an A. Alright, so now we're trying to find how can I get this sector to equal the whole area of this sector. That's the thing. What sort of ratio do I need to get it equal to this? What portion of this do I need? And obviously, if I add up enough of the same sector, it will equal of this area, right? But just by how much do I need to do that? And the way to find out is to, I'm not really find out, but if you think about it, some amount of this angle theta that's made, because remember, oh, okay, so thing is that when I was trying this on Desmos, this x3 wasn't actually some random x3, it was actually x2, like the positive version of x2, right? So the way I did it was, since x2 is a part of the sector right here, or like a part of angle right here, I just used, how should I say this? Got the angle between here, and used the angle of the sector, so let's call this angle sector, over angle, smaller angle, new angle, wait, no, I think it's, let me check. Oh yeah, so it should be smaller, the smaller angle should be on the bottom, and the bigger angle should be on the top, and yeah, I why though? Well, I don't freaking know. But, this sector is basically the same ratio, it's proportional, or equivalent to the ratio of angles, right? Because it shares the angle, but it's just proportional, it's actually a fraction. So this new angle is going to be, this kind of does make sense, that this new angle is cutting out parts of the bigger angle, but it works. I mean, you'd think it'd be dn over data s, but that's just telling you the ratio between the old versus new, but we're trying to get from new versus old, that's how you flip it, you know? So to get from new to old, we have to flip the previous reading, and I just had it there. Oh, they lost there. So yeah. So how are you gonna find this angle? How are you gonna find the old versus new? Well, last video I showed you how to get the old angle, how to get the new angle, same method. But yeah, same method, but it's a little different. So you have this angle right here, actually. So you have this angle right here, and this bigger angle that is encompassing both angles, right? And we want only just this angle. So we just do theta 2, which is this bigger one, theta 2, minus theta 1 equals the smaller theta mu, let's say that. And the thing about this new angle, you're gonna do the arctan, whatever, the arc cosine. But in my practice, since this smaller angle, which is x2, because I was trying to find an equation, on this large sector, but easier. I didn't want to include this part with the negatives. So if you don't want the negatives, just find the difference between the angles of the sector x2 and x1, the actual angle, this angle, which is right here, and then divided by the actual angle, which, if you really think about it, the equation on top was pi minus angle, this angle 2, this angle 1. This was angle 2 plus angle 1. And on the bottom, it's angle 2 minus angle 1. It's kind of weird, but you know. Yeah, so what I did on Desmos is I just flipped this part off the other side, so yeah. Anyways, just use this ratio and multiply it between here, theta O or theta mu, and you get the same result as the previous thing. You know. 2 minutes left. 22 minutes. Yeah, I'm gonna just say it's probably a lot less work if you just did it normally, like last video, instead of doing it like this, because the only idea is to actually find both angles, which is tedious, and use arctan or cosine, whatever. And then you still need to make an integral, still need to do that, still need to find slope, still need to, it's like so much more work. But like, I don't care. This makes, like, I don't know, it felt like doing something that my time, and I wasted my time finding this, even though the other biggest equation was just a lot better. Yeah. Alright, that's it for the part.